Hello, I am Somnath Dasgupta. I teach at Jamia Millia Islamia, New Delhi. Today we are going to learn about Nesosilicates, in particular two important members, olivine and garnet. Before we start about Nesosilicates, let us talk a little bit about the structure of silicate minerals in general. The basic building blocks of any silicate structure are SiO4 tetrahedra, where silicon sits at the center of a tetrahedron with 4 apical oxygens. In figure 1, you can see the SiO4 tetrahedra, which are considered to be the building blocks of any silicate structure. Here, the blue silicon atom, which is much smaller, sits at the center of the tetrahedron, and the buff colored 4 oxygen atoms are sitting in the apex. SiO4 tetrahedra can remain isolated with respect to adjoining tetrahedra, or may be linked with adjoining tetrahedra with the help of sharing apical oxygen atoms. When they remain isolated, we call them Nesosilicates, which is the focus of the present module. However, if the adjoining SiO4 tetrahedra are linked together sharing 2 oxygen atoms, the structure is produced, we call it single chain inosilicate, example pyroxenes, or double chain inosilicates, example amphibole. If 3 oxygen atoms are shared, we get sheet silicates, example being mica. If all the 4 oxygen atoms are shared, we get tectosilicates, example being quartz and feldspar. Now, Nesosilicates, as I said, is characterized by isolation of the SiO4 tetrahedra. They remain isolated with respect to each other. Olivine and garnet are the 2 very important groups of minerals within the Nesosilicates. Let us start with olivine. Olivine crystallizes in the orthorhombic system. Olivine has a wide range of composition, but the most common type of olivine is called the MgFe olivine group of minerals, or alpha olivine. The 2 major end members of the MgFe olivines are forsterite, Mg2SiO4, and fayalite, Fe2SiO4. There is the structure of olivine, MgFe olivine or alpha olivine, consists of isolated SiO4 tetrahedra, which are linked with MgFeO6 octahedra, where you can see that SiO4 tetrahedra are in blue and violet, while the MgFeO6 octahedra are in green and yellow. And this is how the SiO4 tetrahedra are linked with MgFeO6 octahedra, but you can notice that the SiO4 tetrahedra themselves are not linked with each other, which is the characteristic of Nesosilicates. Now, within this MgFeO6 octahedra, there are 2 equivalent octahedral cation sites, which we call M1 and M2. M1 and M2 are occupied by magnesium and iron, and there is usually a complete disorder in between M1 and M2. I mean, Mg and Fe can randomly occupy either the M1 site or the M2 site. Now, coming to the chemistry of the MgFe olivines. As I said, Mg2SiO4 is called forsterite, Fe2SiO4 is called fayalite. and there is complete disorder between Mg and Fe in the two octahedral sites. I shall explain in the text in figures 3 to 5 the details of the structure of olivine. Now, optically, all olivine minerals are having very high refractive indices, very high 2V, very high dispersion, very high density, as well as hardness. There is a beautiful correlation between the optical and physical properties within the MgFe olivine series with composition, and we can easily determine the composition of olivine species with the help of optical and physical properties. However, with the advent of electron probe microanalyzer, we can also determine in situ composition of olivine minerals on a micro scale. Now, in addition to MgFe, the olivines of the alpha olivine series may also contain some minor elements. For example, manganese and calcium may be present in small amounts in iron olivine. Chromium and nickel can occur in small amounts in magnesium olivine. Also, some magnesium olivines may contain platinum group elements in trace content. There is a complete solid solution between forsterite and fayalite, which is shown in figure 6. In this diagram, you can see very easily that the liquidus temperature of forsterite is higher than that of fayalite. As you can see, the liquidus temperature of fayalite is higher than that of forsterite is higher than that of fayalite, and the loop shows that there is a complete solid solution with the liquidus on the top and the solidus on the bottom. Now, coming to the occurrence of olivine. Olivine commonly occurs in ultrabasic rocks, but may also occur in basic igneous rocks. We get olivines in ultrabasic nodules in alkali basalts. We get olivine in ophiolite complexes, and olivine is supposed to be the most important and major constituent of the Earth's mantle. One of the very interesting feature of olivine is that with increase in pressure, which corresponds to increase in depth within the earth, olivine changes the structure. For example, at a pressures corresponding to a depth of 410 kilometers within the earth, alpha olivine changes to beta olivine, which has also a formal name, Warsleite. Warsleite is basically a synthetic mineral, but is also found in some meteorites. Warsleite is also orthorhombic, but the most important point about the structure of Warsleite is that it has the capacity to host hydroxyl ion. This would imply the presence of water in the mantle. That is a very interesting topic of research. At a depth of 525 kilometers, Warsleite changes to gamma olivine. So to say, we have a transition from beta olivine to gamma olivine. Gamma olivine has a formal name. It is called ringudite, and it is cubic in structure. So it is no longer orthorhombic as such as alpha or beta olivine. The important point regarding ringudite is that it also has the capacity to host hydroxyl ions. So the structural characterization of both beta and gamma olivine are of immense importance. They have been done in details and they provide information about the seismic discontinuities that we have within the earth. For example, three major seismic discontinuities within the earth are at 410 kilometers, which corresponds to the conversion of alpha olivine to beta olivine, at 525 kilometers, which corresponds to the conversion of beta olivine to gamma olivine, and at 660 kilometers, which corresponds to breakdown of gamma olivine to magnesium perovskite and periclase. The phase transitions in the Earth's mantle are shown in figure 12, and as you can see, the conversion of alpha Mg2SiO4 to beta olivine occurs at around 410 kilometers, followed by a change at 525 kilometers where beta olivine is converted to gamma olivine, and then at 660 kilometers depth, gamma olivine breaks down to magnesium periclase and magnesium perovskite. So the seismic discontinuities are due to the transformation in the olivine structure. Besides the MgFe olivines, there are some other types of olivines found occasionally in rocks. These are the manganese olivine tephroite Mn2SiO4 and MnFe olivine nebelite MnFe2SiO4. Other rare species include monticelite, glaucocrite, and other species. Basically, this is the story about the olivine group of minerals. As I said at the beginning, the other important member of the Nesosilicate is the garnet group of minerals. Garnet group of minerals are described under two different solid solution series. Basically, these are called pyrrolspite garnet and ugrandite garnet. Pyrrolspite garnet comprises of three species: pyro, MgAl garnet, almandine, iron aluminium garnet, and spessartine manganese aluminium garnet. In ugrandite, we have three important species. These are uvarobite, which is chromium calcium garnet. Then we have andradite, which is trivalent iron calcium garnet, and we have grossular, which is calcium aluminium garnet. The important thing is that there is complete solid solution within the pyrrolspite and ugrandite series, but there is limited solid solution between the two series. The garnet is isometric, so to say it crystallizes in the cubic system and is therefore isotropic under Frost-Nichols. Garnet structure consists of alternating SiO4 tetrahedra and MO6 octahedra. By M here I mean the trivalent cations. These alternations produce a three-dimensional network within which there are cavities, and these cavities are filled up by the dodecahedra of divalent cations. You can see the details of the garnet structure in figure 14. In figure 14, I am showing the garnet unit cell where I talked about the alternating SiO4 tetrahedra and the MO6 octahedra, which are shown here with forming a three-dimensional network within the cavities occur the divalent cations in dodecahedral coordination. This blue, these ones, these green ones are the divalent cations which occur between the SiO4 tetrahedra, which are given in blue, and the buff colored MO6 octahedra, forming a three-dimensional network. And this divalent cations are sitting in the cavities in dodecahedral coordination. The Garnet group of minerals occur very commonly in various kinds of rocks, particularly in metamorphic rocks. I will come to that occurrence part later, but let me say something about the optical properties of the Garnet group of minerals. Just like olivine, there is an excellent correlation between the optical and physical properties with composition within the pyrrole-spiked garnet. Again, the problem is that with the advent of electron probe microanalyzer, we are more commonly these days determining the composition directly rather than interpreting with the help of optical and physical parameters. The Garnet group of minerals have a very characteristic property of having different kinds of zoning, which are used for many petrogenetic interpretations. Basically, we have two kinds of zoning. One is called growth zoning, where the zoning occurs or forms during the growth of the garnet crystal. Or there can be a second type of zoning which we call diffusion zoning. Diffusion zoning forms during cooling from high temperature. Garnet occurs in metamorphic rocks commonly, particularly in the Barrovian facies series. The garnet zone is defined on the basis of appearance of almandine-rich garnet. Pyrope-rich garnet occurs in very high pressure rocks, and andradite occurs in calc-silicate rocks mainly, and where it forms solid solution with grossular, and therefore we often refer them as grandite garnet. Spessartine is common in manganese bearing rocks at relatively low temperatures. Garnet, almandine rich garnet, may occur also as phenocrysts in some basic igneous rocks as well. Another important compositional aspect of garnet is that in some varieties presence of water has been detected. This species is called hydrogrossular, and this hydrogrossular is found in altered basic rocks and skarn deposits. This is a very broad overview of the nesosilicates, particularly the olivine and the garnet group of minerals. Obviously, you will refer to the text while listening to this. You can see that I have not described in details many figures which are produced in the text, simply because if you look at the caption and if you look at the notations within the figure, you can very easily understand what they represent. So, in summary, I have tried to highlight the salient points about the olivine and the garnet group of minerals, which are very important constituents of the nesosilicates. But please remember that other than olivine and garnet, there are other nesosilicates which will be described in separate modules. The important point to note here is that both olivine and garnet are major rock forming minerals, and they are widely used as petrogenetic indicators. So, it is not merely the optical physical properties, but their petrogenetic significance must be understood. Now, I have refer to some figures in the presentation, but not all, as you will see in the text which accompanies the presentation. There are other figures, but I have very carefully tried to give good captions so that you can understand those figures and the notations in the figures. So it will not be difficult for you to understand the figures and correlate with this presentation. However, I will add to some clarifications to some of the major figures in the text. I hope you enjoyed it. Thank you very much.